Hi guys, Miss O'Connell here. So this activity is a little bit shorter, this lab activity, so I'm going to record the directions in one video. Okay, so the goal of this activity here is to determine the rate of circular motion and which variables that rate relies on. So we learned an equation, right? We can calculate the tangential velocity, but we want to figure out which variables can actually vary when an object rotates around a circular path. Okay, and when those variables vary, what happens to the rate of the object as it moves along that path? So some background information to review and recap what we've previously talked about. Uniform circular motion means that the object has the same speed as it moves around a circle. So the speed is constant, the direction changes at every instant. Okay? There are many examples of uniform circular motion, okay, which we see in our everyday life. A car moving on a circular track at 50 miles per hour, a child on a merry-go-round at an amusement park, the moon orbiting the Earth, okay, roughly. It's basically an elliptical path, but we can model it pretty accurately using circular motion. The speed tells us how fast an object is moving, or in this case, rotating, while the velocity tells us how fast, but also in which direction the object is moving. Velocity is therefore said to be a vector, represented by an arrow, okay, and a line segment. The velocity vector of a moving object in a circle depends on where the object is in that path. It's always tangent to that circular path, as shown in the figure to the right here. Here, the length of the vector is always the same, since the speed is constant as the object moves around the circular path. Okay, so these vectors here in this image, they represent the tangential velocity, okay, which is the speed of the object as it moves around the circle. Notice that the length of these vectors are equivalent, right? The length or the magnitude of the vectors are equivalent, which means that the speed stays the same. But you can see what changes here is that the direction of the arrowhead points in a slightly different direction depending on where in the path the object is located. Okay, so the speed is constant, but the direction is changing. Therefore, technically the velocity changes, but the magnitude of that velocity stays the same. Using a digital simulation, okay, we usually take our tumble buggies and tie them to a rope and have them circle around us in the hallway. We unfortunately don't have tumble buggies at our house, so we're going to use a simulation to do this instead. So we have a simulation of a ball that's experiencing uniform circular motion. We're going to use this simulation to determine the tangential velocity of this object at 4 different radii. Okay, so at 4 different distances from the center of the circle, we're going to see how the tangential velocity changes. You're going to do this by collecting data using the simulation. Okay, so in order to examine the relationship between the radii of the circle and the tangential velocity, you'll use the sliders to adjust the radius of the path and record the data in the table below. Okay, so the purpose here, you're going to take a look at this sentence here and determine what is your purpose. What is the goal of this experiment? So I suggest that you pause the video and you fill out purpose and give the hypothesis a shot. So pause the video. Okay, so our purpose here we see is to determine how the tangential velocity will vary over 4 different radii. So the hypothesis is, what do you think is going to happen? Okay, so a hypothesis should be in an if then because statement. If independent variable, then dependent variable, because why you think so, the prediction, right? An independent variable, we remember, is what? What's an independent variable? An independent variable is a variable that you change or is changed during the experiment. The variable that's changed, use the slider to adjust the radius of the path. We're doing that 4 times, okay? So the independent variable is the radius. So if the radius of the circular path length, okay, so what are you doing to it? Are you going to increase it? Are you going to decrease it? Okay, it's going to change, quite obviously, because you need 4 different radii. So it's up to you whether you're going to start at a low radius and increase it, start at a high radius and decrease it. So in that blank can be increase or decrease. If the radius of the circular path increases, if the radius of the circular path decreases, then which variable are we measuring the impact on? The tangential velocity. So you should have, if the radius of the circular path increases, then the tangential velocity blank. So you're going to say whether it's going to increase, decrease, stay the same. So you're going to fill in that blank with either increase, decrease, or stay the same. Because, explain why you think so. Okay, so if you're not sure, you can think about what we know about tangential velocity. We know that it's the constant speed at which an object moves in a circle. We also know that we can calculate it by taking the circumference and dividing by the period, 2 pi r divided by the period. Okay, we can also calculate it if we have the centripetal acceleration. In this case, we don't yet. Okay, we're not sure yet based on the simulation. So you want to think about this equation here if you're really lost. Okay, so think about when radius increases, what do we think will happen to the tangential velocity? And then explain why you think so. So pause the video, complete the hypothesis statement, unpause when you're ready to go. Okay, so using the simulation, which is actually linked right here, it's going to open it up for you. Okay, you'll click on it once it loads and make it full screen. What you need to do in the data table, right? It tells you to adjust the radius of the path and record the data below. Okay, so there's a note on the data collection. The radius is measured in meters. Okay, it's the distance from the center of the path to the outside of the circle. Circumference is the distance around the circle that's traveled, given by the equation 2 pi r, where r is the radius. So using the simulation, you're going to calculate circumference, record radius, and record the speed. We're going to record the speed just in meters per second. So using the simulation, okay, I'm going to do one example with you guys. So here's my simulation. I want to click velocity vector and acceleration vector, just to remind myself that the acceleration is center seeking and the velocity is tangent to the circular path. I'm going to record my radius. So I'm going to start with 30 meters. To find the circumference, right, we have circumference equals 2 times pi times radius, which gives us the distance traveled around the path when it makes one cycle. So I'll take 2 pi times 30. You can leave that in terms of pi or as a decimal. It might be easier to type the decimal in, but technically the choice is yours. I'm going to round that to 1 decimal place, so I get 188.49, which I'm going to round to 0.5 meters. So I'll type that in here. Okay, once I've calculated the circumference, I'll head back to my simulation, and I will click Start. It's going to trace the circular path of the object as it moves around the circle, and it's going to adjust and give you the speed. Okay, so you'll record that speed. It gives it to you. You don't actually have to calculate it. So in this case, we're just looking at the data and we are analyzing the data. Okay, so it traveled technically around one cycle. It'll travel 188.5 meters. Its tangential velocity is 20 meters per second when it has a radius of 30. Okay, you'll then either increase or decrease the radius, up to you. So then I'd head back to my simulation. I'm going to increase the radius and do the same exact thing. You want to leave the mass constant. Okay, so no need to change the mass. You're changing the radius. You're pressing play. You're going to record tangential velocity and radius for 4 different data points. Using those 4 data points, you're going to answer analysis question 1 and 2. Analysis question 1 asks you to use data from the table. Data means numbers, so you should be using numbers from the table to answer this question. You're going to explain how the radius of the circle impacts the tangential velocity. So basically, you're going to analyze your hypothesis, the prediction that you made. When you increase the radius, does tangential velocity increase, decrease, or stay constant? Okay, and there's some guiding questions to help you there. When radius increases, what happens to the value for tangential velocity? When radius is constant or consistent, what happens to the value for tangential velocity? Okay, you're going to use data, numbers from that table to answer that question. The second question is you're going to define what uniform circular motion is, which is in your notes, in the multiple videos from last week, and also in the background information. So define what uniform circular motion is, and use the data to determine if this object is moving with uniform circular motion. So define what it is, and then based on the data, support, okay, or refute that this object is moving in a uniform circular motion. Okay, and then there are 2 extension questions, which you're going to need to use the simulation to answer. Okay, if you have any questions here, I have extra help on Tuesdays, Thursdays, and Fridays from 2:30 to 3:15. Okay, if those don't work for you, you need another time, just let me know and we can set up a Google Meet at any point. I will be in the Google Meet, or in a Google Meet, rather, that's linked in your classroom for the last 20 minutes of your class if you do have any questions. I will talk to you guys tomorrow. I hope that you're having a great Monday, and I will talk to you soon.